Let's talk about the general procedure for applying either Poisson's equation or Laplace's equation. So we've kind of talked about this briefly at the end of the previous video, but our first step is going to be to solve the Laplace or Poisson equation. And so there's sort of two routes we can take depending on the problem. One, we're going to be using direct integration, and so this is if our voltage is only a function of one variable. And so it turns out that this is going to be a lot easier, and this is what we're going to be focusing on in this unit. However, there is another case where we'll have to separate and then integrate, and that's if our v is a function of more than one variable. This gets really messy really quickly, and because we have a lot of other topics to cover at the time of recording this video, we're not going to focus on that. But you can look at some of the examples in the textbook to get an idea of how this is done. So after we've solved Laplace's equation, our second step is going to be to apply our boundary conditions to determine the integration constants from step one. And so what this is going to do is this is going to make our solution unique. So this makes the solution unique, as I discussed at the end of the previous video where we were talking about our uniqueness theorem. And so finally, once we have our v equation, we can find other parameters of interest. And so at this point, we have a lot of equations in our sort of toolbox. So for instance, if we wanted to know our electric field, we know that that's going to be negative gradient of v. Once we know our electric field, we can then find our electric flux density pretty easily just by multiplying by the permittivity. And so again, keep in mind this is our updated permittivity, which is equal to epsilon naught times epsilon r. With our electric field, we can also find our current density J from our point form of Ohm's law. So we know that J is equal to sigma times E. And so of course, this is assuming that we know something about the material, the relative permittivity, or the conduction. So we have some other things that we could find as well. So this is sort of one area. We could focus on our electric field. We can also find the charge induced on a conductor. So charge induced on a conductor. Well, how can we find that charge? Well, ultimately, remember, our charge on a conductor, if it's a conductor, all the charge is going to be on the surface. Remember, it has no charge in the volume. So we can say Q is equal to the surface integral of the surface density of the charge over the surface. Okay, well that's pretty straightforward, but how do we figure out what that rho s is? Well, our rho s is just going to be equal to dN, the normal component of our electric flux density. And so that's something that we saw when we were talking about our boundary conditions in the previous unit. So you can look on page 202 if you want a refresher for that. So with this charge information, so once we have charge and of course we started with our voltage, we can then begin to talk about capacitance. And so we're going to come back in some later videos and we're going to talk some more about capacitance. But in general, we know that our capacitance is going to be equal to charge divided by voltage. So of course, we started by solving for our voltage, and now we have our charge as well. So one last area, well actually a couple more areas, but sort of really brief for both of them. So our second to last area is our current. And we know that our current is going to be the surface integral of our J dot ds, where of course we found our J up here from our electric field. And so once we know our current and our voltage, we can start talking about resistances. And so what we're going to do a little later on in this unit is we're going to come back to that case of a non-uniform resistance. So if we have some non-uniform cross-sectional area, for example, because we know that in general, our resistance is going to be equal to voltage over current, where we have our voltage, of course, is what we found initially, and our current we can get from this expression, where we had our J from this expression up here. So the final thing then is our force. So we can say our force is just equal to the charge times our electric field. And so from there, we can relate it to other parameters as well. So as we're going to see in the example in the next video, we can relate this force to pressure, for instance. So we're not limited to just these items shown here, but these are usually what we're going to be interested in.